Counting sort is a sorting algorithm that works by counting the occurrences of each unique element in the input array. It then uses this count information to place the elements in the correct sorted position. Counting sorting is a non-comparative sorting algorithm that excels at sorting a collection of items when the range of value is known and relatively small. It leverages the power of counting to efficiently arrange elements in ascending order.
So this is an example of an array. So the total number of elements in this array is 17 and indexes from 0 to 16. And key value is the range. You can check out the minimum is 0 and the maximum is 9. So the value range is from 0 to 9 and the key value is 9. So the first step is we're going to count the elements having the string k values. So how many times that elements is in the array? After counting, you're going to store the elements. Before storing the count, we're going to take another array. And we're going to count the elements in the array and put it in a new array. So the first element is 2 and we're going to find the index 2 in the new array. And then increment the value, so it's now 1. So find the index 1 and put it in the index 1. Next, find the increment the index 1, so it's now 2. So 0, find the index 0, so put it in the 0. So 1. So continue the process until all the elements are counted and put it in the new array. And after counting, you need to find the correct position of these elements in the sorted array. So we are going to update this new array, so we name it as a count array, such that this count array contains the actual position of the elements. So how we are going to do that? So we are going to update this array. So the first value of the updated array will be the same in the counted array. So the value of the first is 3, index 0, and then the index 1 will in the index 0. So we need to plus this to get the correct position of the array. So 3 plus 3 is 6, and then 6 plus 4 is 10. So we continue the process until in the last elements. And now we're going to get the sorted array having the same number element, which is 17 and index of 0 to 16. And how we are going to fill this array. So from the original array, we're going to scan from the right to left. So start from the value of 9. So what you have to do is, in the count updated array, you are just to go to index 9 because the value is 9, but we cannot store 9 at 17 because we don't have index 17. So we are working in the index, so we are going to decrement the value by 1. 17 minus 1 is 16. So put the element 9 in the index 16. So increment, we are now in the value 1. So in updated counted array, it is in the index 6, but we are going to store it in index 5, so we're going to decrement 6, so 6 minus 1, so it is now in 5. So store the value 1 in index 5, so we are now in the value 0, so value 0 is in the index 3. So index 3 is minus 1, so it is now in the index 2, so put value 0 in the index 2. So next, the value 2, so 2 is in the index 10, and 10 minus 1 is 9, so the value 2 is in the index 9. So put the value 2 in the index 9. So continue the process until you all sorted the elements and put it in the correct position. So putting all the value in the correct position of the sorted array. And now we have the sorted array using a counting sort.
Counting sort is practical in real-world scenarios. For example, it can sort student grades from 0 to 100 or organize votes by candidates' IDs. Imagine arranging the days of a month 1 to 31. Let's look at a test case. Sorting student grades input 90, 85, 90, 75, 85, 100, and 70. Where the output must be 70, 70, 85, 85, 90, 90, 100.
And now, let's use counting algorithm into a real-world problem. Here we have a student grade. First student got 90, second student got 85, third student 90, fourth student 70, fifth student 85, and last student 100. And how we can sort it into unsorted to sorted by using counting algorithm. First, get the lowest to highest element. So 70, 85, 90, 100. So our n log or n is 6 because it has total of 6 elements given, and 70 to 100 also our key word is 100. First 90, so put it 1 to 90, 85 put 1 into 85, 90 so 1 become 2, 70 put 1, 85 so 85 has 1 so it become 2, and last 100 put 1. So in total 70 get 1, 85 in total of 2, 90 is equivalent to 2, and 100 is equivalent to 1. Let's put count in a first statement. And next step, we need to update the count element. 1 plus 1 is equal to 3. 3 plus 2 is equal to 5. 5 plus 1 is equal to 6. Let's proceed to the last step. Let's start to 100. In 100 is into a 6, so 6 minus 1 is equal to 5. Put 100 to 5. Next 85, so 85 is in 3, so 3 minus 1 is equal to 2, so 85 is in 2. Next 70 has 1, so 1 minus 1 is equal to 0. Put 70 into 0. Next 90, back to 90, so 90 got 5, so 5 minus 1 is equal to 4. Put 90 into 4. Next 85, back to 85, so 85 is 2. 2 minus 1 is equal to 1. Put 85 to 1, and last 90, back to 90. 90 get 4, so 4 minus 1 is equal to 3, so 90 is in 3, so it was finally sorted. With that, the final output are 70, 85, 85, 90, 90, 100. So that's how counting algorithm work into a real world problem.
In our simulations, counting sort effectively handled small range numbers. Showcasing time complexity 0n plus k, it demonstrated stability, equal elements, retained their original order. This efficiency highlights why counting sort is ideal for specific use cases. However, like all the algorithm, it has its limitation, and the next section will discuss the strengths and challenges of these methods. For the result and observation, when tested against quick sort and merge sort, counting sort outperformed them in execution time for small range inputs. However, as the range grew, its memory usage increased significantly. This comparison shows counting sort excels in a specific condition, but is it always the optimal choice? So counting algorithm have a several strengths. It's incredibly fast for small range inputs, provides stable sorting, and is simple to implement for integers or item mapped to integers. These features make it a go-to algorithm for sorting grades, votes, or calendar dates. Despite its strength, counting sort isn't perfect. It struggles with large ranges due to high memory usage. It is also unsuitable for floating point numbers or negative values unless modified. These challenges mean it's not the best choice for all scenarios. Understanding these drawbacks ensures you use it effectively in the right situations. Now, we're done explaining and simulating the counting algorithm. Now you know how it works. In this part, we'll test your knowledge. Take a moment to solve this problem yourself. Try sorting the fruits using the counting algorithm we discussed. The problem is, we have the following fruits and what respective number of pieces. Where the banana has 100 pieces, orange has 50 pieces, apple has 50 pieces, strawberry has 70 pieces, coconut has 30 pieces, and lastly grapes has 50 pieces. Your task is to sort these fruits by the number of pieces from smallest to largest. Good luck and happy sorting!